assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
Okay, to solve this, we're going to use the Rydberg equation, and we are given that m equals 5, since the question says that the electron is dropping down to the 5th level. So the longest wavelengths are going to be when an electron drops down, an electron drops down from 6 to 5 and 7 to 5. Great. So let's find the wavelength. By using the Rydberg equation, we can just plug in what we know. I'm going to put up here that R is equal to 1.0974 times 10 to the negative second, just so I don't have to keep writing it because it's a little bit long. Okay, great. So we have R, and then we know our M is 5, so 5 squared. And let's do the first wavelength, which we'll say is 6. We'll say 6 squared. So calculating this all out, you should get a wavelength of 7,458 nanometers. And we're going to do the exact same thing for our next line, which is 7 dropping to 5. Again, we have our 1 over wavelength equals R. And we know our M is not going to change because we're told the electron drops down to the 5th level each time, and then 1 over 7 squared. And this will give you a wavelength of 4,653 nanometers. All right, now that we have our wavelengths, we can use the equation E equals hc over wavelength. So we know that h is Planck's constant and c is the speed of light, and then we just solve for the wavelength. So let's give it a try for 6 dropping to 5. So we know the wavelength is 7,458. So let's say E is equal to Planck's constant, which is 6.6 times 10 to the negative 34th. I'm going to leave out my units just for time's sake, but you should always include your units. And then we know that the speed of light is 3 times 10 to the 8th. And then we know we want our final answer to be in moles. So we're going to multiply this by Avogadro's number, because Avogadro's number units are photons, since we're dealing with energy in this case. Photons per mole. So this will give our answer, it'll put our answer into moles. So we're going to multiply this by Avogadro's number, which is 6.02 times 10 to the 23rd. And then we're going to divide this by our wavelength, which we said was 7,453 nanometers. So we know that our speed of light is in meters, so we want our wavelength to also be in meters. So since this is in nanometers, we're just going to go ahead and multiply that by 10 to the negative 9th. And then once we calculate that out, oh, and you know what? We know that Planck's constant is in joules, and we want our final answer to be in kilojoules. So we're just going to say 1 kilojoule is equal to 1,000 joules. So that's just added on the end so we can get our final answer into kilojoules. You could also just calculate this part out and then divide by 1,000. So you should get that energy equals 16.04 kilojoules per mole. Great. So we're going to do the exact same thing with our second line. So I'm just going to go ahead and erase this so I don't have to write it all over again. So, oops, that's not what I wanted to do. There we go. So we're going to have the same exact structure. The only thing we're changing in this case is the wavelength. So we're going to use our second wavelength, which was 4,653. And again, we want it to be in meters, so we're going to say times 10 to the negative 9th, which will give us meters. And that is going to equal E equals 25.7 kilojoules per mole. And these are both going to be in the infrared region of the electromagnetic spectrum. The best way to look that up is to pull up your electromagnetic spectrum and then match the wavelength to the electromagnetic spectrum.